Hello, everybody. As promised, let's have a look at the finally at the application of a convolutional neural network on the MNIST dataset, as we've seen in the lecture last week, the theory we've seen last week. Today we're going to run we're going to run the we're going to construct a convolutional neural network and run on the MNIST dataset. So I'm assuming that you have Keras installed on your computer, and let me just set my environment here, my working environment. Okay, so I'm assuming that you have Keras installed. So if you're running on the university computers, Keras is installed. You're gonna have no problem to do this. I'm still having trouble with my environment. Let's see. Okay, this should do. Right. So okay. So this we are importing Keras datasets. We are importing the MNIST dataset, which is the dataset of handwritten postal information from the US Department. And we are creating already, the MNIST is divided into training set. So I put in the X training set, which is basically pictures now. We're not talking about feature vectors anymore. And these are the label, the classes for the training set. And it's also divided into test set. This amounts to, if I remember well, it's 60,000 training examples and 10,000 test examples. So I'm loading the data from this MNIST data set that already comes with the Keras installation. Then we are loading into training set and test set. So let's run this to see if we have it. Yes, we have it. Now, we can actually see the size of the training set. Let's see, xtrain dot shape. It's exactly 60,000. And these are pictures of 28 pixels by 28 pixels. We can have a look at one of these pixels, one of these pictures. Let's see the first one. The first one, see just the first element of this vector. It's just a background with some foreground pixels. It's not very illustrative, but we can actually see the figure by using our world famous, that we are already well acquainted of, Matplotlib library. So let's load Matplotlib library. Now, we can see then xtrain, the first image. What is the shape of that? Dot shape. That is 28 by 28. Now TLT imshow. Let's look at this first image, how it looks like. Let's see that in grayscale. CMap equal to gray. And here we have. There is a number, a very badly written number, which sort of looks like a number 5, right? We can check what is the label for this. Let's see for this. Let's see if I can still read handwritten digits. Yes. So the label of this squiggle here is 5. So this represents a number 5 in the test, in the training set. We can also have a look at the entire training set. Let's see the entire training set. So these are actually, this is our number 5. Then the second image is a number 0 and 4 and so on and so forth. And the same thing we can do for the the test set. Test set is already labeled. Now there is an issue here. So if we feed it in a convolutional neural network, if we feed the labels like this, the convolutional neural network is gonna try to find a function that will give as output a sequence of numbers, and that's not what we want. We want to work on categorical data. That's a multi-class classification. Why multi-class? Because I have to classify every scribble that looks like 7 as a digit 7, everything that looks like a number 2 as number 2, and so on and so forth. So MNIST is given this as entry data, entry labels. We have to transform it to categorical data. Again, let's go back to our nice Keras utils, np utils, import to categorical. Yep, so I've written it right. Now I have to, let's try a test here. Let's see, let's call it Y example. We use to categorical. So I trained that. Let's see now Y example. Now that's I'm changing this these labels to what is called as one-hot encoded. One-hot encoded, meaning that 0 will have nothing. Actually, we'll no. The first item is a 5, right? We can't see it here, but there will be a number 1 on the 5. Remember, this second one is a 0. We're talking about the Y training. We're changing the Y training set. If you remember, then the Y training set, the second item was the second label was a 0, so it will have a 1 on the label, a 1 in the position 0, and this has 10. This is a matrix of each element of the matrix is a vector of 10, representing the 10 digits. So this is called, let's add here, one hot encoding, because otherwise the neural network is going to think that we have a regression problem and not a classification problem. Right, so so now we have to do the same for everything. So let's call Y categorical test. We use two categorical Y test 10. And also Y categorical train to 2 categorical Y train 10. Now I'm placing the labels. All the labels now are transformed. Even the labels from the test data and from the training data will be a one-hot encoding. Now the next step is that in order to help the processing of the neural network, it's always good to normalize the X data. So it's always good to have your input data as varying from 1 to 0, not dealing with large values. So we can get, we know that this data set runs, the images are encoded from 0 to 255. We can check that, just get any image here. Let's see, X train. 0 max. Oops. X train. Train max. 255. That's the maximum, and if we get the minimum, this is I'm just using one image as example, but all the images are going to go run from 255, from 0 to 255. So what I'm going to do here is to transform the whole training set. X train will be equal to X train divided by 255, and the same thing for X test equals to X test 255. Now we can see X train minimum will be a floating point now, right? Because I'm dividing and transforming everything to floating point. Let's see, the maximum is 1. Right. So we can use that and see the image plt im show to see that we still have the same kind of image. X train 0. That's the image, just the encoding around. I just couldn't be bothered to make it at I could make a CMAP just to see that nothing changed. All good here, all good. Now we've seen that the training set X train dot shape. It's a matrix of 60,000 elements, where each element is a 28 by 28 matrix. These are images. The X test is the same, I hope, but not with 60,000, but with 10,000. But it would be good to reshape to include the channel. So let's see here, reshape to include the channel. We do that by, we've done that before, but we can do that again. X train, let's get X train reshape to 60,000 by 28 by 28, and as it's a grayscale image, it has one channel. And this way now, this can be easily applied to a 3-channel image, to an RGB image. Okay, now we have the shape of my data is a 4-place structure, and this represents the channel of this structure. Okay, as I said many times, that's data science for you. We've spent, what, 20 minutes just massaging the data. Now comes the nice bit, the interesting part, which is training the model, or constructing the model, rather. Constructing the model. Constructing the model. It's very similar to what we did last week. We get from Keras models, import sequential. Why do I need to import sequential if you're dealing with a convolutional neural network? Remember from last week that I said that at the end of the convolutional neural network, we want to do classification, right? And classification, the classification part is done by densely connected, multiply connected neural network that is appended at the end of the whole architecture of a CNN. The convolutional part is used to learn the features, but the classification is still done like we've seen last week on a multiply connected neural network. So we still need to have a sequential model. But now, last week, the sequential model was enough. This week, we need other models as well. From layers, import dense convolutional 2D, max pool 2D. Remember the pooling layers that I said there was one that was max? It just takes the max of a neighborhood. That's the max pool. And this is the 2D, two-dimensional convolution. You have three-dimensional convolutional, any n-dimensional convolutional layers, but we are just going to use a two-dimensional because we have two-dimensional images. And flatten is a function that we're going to use to transform our images at the end as a vector so that it becomes input to a multiply connected neural network. All loaded. Now let's construct our model. Model will be sequential. Now we have a convolutional layer. The convolutional layer, then I'll copy and paste here because then it's going to take too long. So basically, I'm adding the same way that we've done before, a convolutional layer, a two-dimensional convolutional layer with 32. What is this 32? With 32 kernels. 32 kernels. Why is that? Because somebody did a whole bunch of experimentation and found out that this data set works with 32, with a convolutional layer of 32 kernels. So this is going to generate 32 feature images. Each kernel will be the size 4 by 4. The input shape is the image, right? It's 28 by 28 with one channel. And remember the activation? We are using the ReLU layer. The ReLU layer. And now this is the convolutional layer. Let's add a pooling layer. Model dot add. Here, as I said, it's a max pool 2D. And usually for simple images, we use a size of 2 by 2, as I said in the theory lecture. Size of 2 by 2. Max pool. Wow, I see. So that's it. We can't live without syntax error. Well do. Okay, so now the flatten, once it will have a first convolutional layer, then a max pooling layer, and then the multiply connected neural network. But in order to go through the multiply connected neural network, I need to model add a flatten function that's going to transform the images obtained from the convolutional and from the max pooling layer into a feature vector. And now our classifier, right? Our classifier. Now our classifier, which is a multiply connected neural network. Multiply connected neural network. Now, okay, so now model add dense And it's going to be a multiply connected network with 128 hidden neurons. Why? Because that works. Activation will be equal to ReLU as well to avoid the gradient vanishing problem. And for the last layer model, last layer should have, how many neurons should have the last layer? If we have 10 classes, I should have 10 neurons. Equation. And for that, I'm going to use a softmax. And now, model, the way to file the model, I'm going to use as loss function, categorical cross entropy optimizer. In this case, last week we used Adam, that's a node optimizer. We are going to use RMS prop. There are loads of optimizers, and the difference is that some run faster than others. And also as metrics, I'm going to use accuracy. Okay, so that's our neural network, our convolutional neural network. Let's see the model. Here is the model. So the first layer is a convolutional layer with 32 kernels. We have to learn 544 parameters for it. Remember that each parameter is one element of the kernel, one value of the kernel. We're actually learning the kernels. Max pooling layer, one flattened layer. Well, it's not a flattened layer, it's a flattened function. Then one densely connected neural network. With 128 neurons, we have to learn quite a lot of parameters. These are the weights and the biases of for each neuron. And the last layer is the output layer, also with its own parameters. Total number of parameters, 591,786 parameters. So we have, it's quite a large neural network for a very simple problem. Very simple problem. The difference is the input of this network is the image. And I'm not doing any human processing apart from selecting the model. The only human processing that I'm doing is to selecting the model, which is quite a lot. But before, up till last week, we were giving the features. We were giving the best features for the network. Now, I really don't care about the features. Well, I do care, but I'll let the network to learn them. Finally, the fun part, which is training the model. Training the model. Then we're going to use model.fit x train y categorical train. Remember, that's not the input because it's not the original input, because it's not a regression problem. Epochs. Just let's be very conservative and just have a few epochs. Otherwise, it's going to take forever. What's wrong here? Model fit x train. Yeah, it's always hard to read this error. Some keys in session flags are not supported this time. Metric. It's complaining about the metric. Let's play here. Metrics. Here we are. Just one S. It's going to take a while. So, well, there's one person watching, the last man standing, Ziwen. Welcome, Ziwen. So you can go for a nap. It's going to take a while. In my computer is quite fast, so it should take about 10 minutes. But let's see, it's fun. It's working. It's fun with him when it's working. Remembering that one epoch is one pass through the entire data set. We are in through the whole network. That's why it's taking so long. It's passing 60,000. Oh, here we go. 60,000 example through this whole bunch of like 500,000 parameters in 2 epochs. Oh, you tried it before. Have you run the MNIST dataset before? So it learned. Now let's evaluate the model. Evaluate the model. Same thing as before. X test. Now remember, we should evaluate with the test set, not with the training set. Model evaluate X categorical test. Right. So do you see what happened here? Help me here, Ziwen. I think he's expecting. I didn't reshape the X test, right? I didn't reshape the X test. Just reshaped the X string. What do you think? X test. Here we go. The good thing is that I don't need to retrain. There it is. We can't escape from silly mistakes. That's the history of humanity. Now, again, from today, I think I'm just copy and paste it. Let's load the metrics. Let's create a set of predictions. You can see what is the prediction. Predictions. What do you think is going to come out? It's just the array. So for every element in the test set, it run the model, it used the model that it's learned here at this step. It used the model to classify each one of the inputs. right? To classify each one of the inputs. So these are the results of the classification procedure. Now, now what I have to do is let's see, model X tests, but we are using the X categorical test, which is one hot encoded. Okay, let's see if we can get it. Now print classification report include Y test predictions. And here we have our precision recall. Right, it's quite good precision recall. It worked quite well. Above 98% of precision recall in F1 score. All worked. Any question, Ziwen? Have you run that before? Where have you run that? Yeah, well, that's the end of the course, right? And yes, 40 minutes. Shall we run this? Shall we do the same thing with the CIFAR data set? Or we call it a day? You are the only one in the room, so you may get to choose. Well, the CIFAR data set, I'll leave it as an exercise, because that's basically the same thing. But we're gonna load another data set, exercise. Run the same with the CIFAR 10 data set. Ah, gosh. Ah, yes, of course, I've shared this notebook. So the data, load the data, because that, I'm not sure if you're gonna find it available. Load the data, I'll give you that. That's the same thing. This data also comes with Keras. Load the data. You can check the shape. Now we have these images are color images, so they have 3 channels RGB. They are RGB images. Let's see one of them. PLT in show X string 0. I'm terrible today, sorry. So this is a frog. Yeah, so it's a kind of ugly frog, but that's how the data set. I'm not going to explain the CIFAR data set. That's the one that I talked about at the end of last week's lecture. There's a bunch of stuff in this data set. Let's pick up 22. Not a frog. Let's pick up 12. A horse. And let's see if I can give you more hints about it. So you have to follow all the steps. Follow all the steps that we've done for the MNIST dataset. But I'll give you the model. I'll give you. Oh, you can run with the same model. Run with the exact same model that we've done in the previous one. Yeah, do exactly the same steps. There is no secret. No secret. You're gonna have, if you run on the same notebook, you can use the same model, but I'd like you to create a new model so that you learn how to do it using the same parameters as defined for the MNIST dataset. Apart from that, do follow the same steps and have fun with this. It's going to work, and basically you're going to follow the steps that we discussed last week in the in our final theoretical lecture, lecture of the course. Yeah, so with this, you train the this data set, and the data set where you're going to be able to identify pictures of cats and dogs and frogs and horses, and also of cars and airplanes. There's buildings. There's quite a lot of stuff on this CIFAR data set. You can have a look. Just it's a famous data set. It's one of the most famous data sets. Let's see if we can open it. It's one that actually originated this whole convolutional neural network. So this is the data set. There is the first is a bunch of airplanes. The second line is cars. The third is birds, cats. So you can train that. And then there's also a test set and training set, but you can use your own images. You can take pictures of your own dog and say, if this network can identify your dog as a dog. You just have to be careful is that the images have to be of the same size. They have to have the same shapes. Otherwise, the neural network is not going to answer on the proper way. Okay, yeah, I think instead of me doing the whole work has been done here. You're going to build the same model with one convolutional layer, one max pool, one flattened layer, 128 neurons, ReLU activation functions. Just follow the steps and train your model with this CIFAR data set and check your results. Your results are not going to be that great. You're basically going to reproduce the results that we discussed last week in the book. That's also described in the book. You're going to need a more complex network to learn the CIFAR data set to have an F1 score above 90%. And you can do some search on the web, do some research yourself, and find a good model that learns properly decipher our data set. Any more questions from the large public that's attending this lecture today? If not, I thank you very much, everyone. Thank you, Ziwen. And I'll see you around. If you have any questions, drop me a line. You should have no problems. As I said, this is just an introduction to machine learning. In order to, you have a good idea now, you have a better idea than you had before. But it's just the beginning. So I just gave you the introduction. I would call it machine learning for computer vision, lecture 1. That's just the basics of it all. There is a lot more to learn, but you have the head start. It should not be that hard. It should not be a magic world for you now. All right? So I will stop recording now, and I'll upload this notebook on our Flow page. And also the notebook that we developed last week, I didn't put on the Flow page, did we? I don't know. I'll check it out, and if not, I'll upload it on the Flow page. Thanks very much, and I'll see you around. Bye.